So I'm Quentin. I've been working at Datadog for the past 3 years, and I'm leading the data engineering team. And today I'm going to talk about how we build highly reliable data pipelines at Datadog. And my hope is that there will be things that we did and learned that can be useful for you all. So I hope that you'll be able to learn a couple of things out of this presentation. Before I dive in, a few words about Datadog for those who never heard of it. So we are a monitoring service for large-scale cloud applications. So we collect metrics from your systems, your databases, your web servers, but also traces and logs. So we give you a global view of your system's health and performance. And you can set up alerts on top of this data to know when something goes wrong in your system. So let me come back to the title of this presentation. I said I was going to talk about reliable data pipelines. So the first question you may have is, what does reliable means? So I asked myself this question, and I came across this definition that I really like, and that I think is the closest to how we see reliability at Datadog. So basically it can be defined as the probability that a system will produce correct outputs up to some given time t. So in other words, you have some time constraints. How can you make sure that you deliver good data in time as much as possible? So what's interesting here is that it doesn't mean that you need to build pipelines that never fail. It's not even possible, right? So you can spend how much time as you want building your pipelines with the best coders, there will still be failures. But it's okay, as long as you can detect the failures early enough and that you have ways to fix them, you'll be able to finish before the deadline and your pipeline will still be reliable in that sense. So with that definition in mind, I'll be talking about how we architect our data pipelines. I will talking about how we monitor the pipelines to make sure that we detect those failures early when they happen. And I will talk a bit about what tools we have in place to cope with these failures and make sure we can fix the issues early enough. Before I dive into this agenda, I wanted to give you an example of an important product feature that is powered by one of our big data pipelines. So as I said in the introduction, we collect metrics data. So this is basically time series data, a collection of data points. Each point is attached to a metric. It has a timestamp, which is when it was sent, a value, and a list of tags that people can use to filter their data in the product. And we keep this data at the highest resolution for at least 15 months in the past, and so people can go back in the past if they want to. They can choose what time frame they want to see. So in this example, they're going to see the past 1 hour, in which case we're going to show 1 point per second. But if they look at the past 5 months, for instance, we're not going to show 1 point per second because that's just too many points on the graph, and it would be unreadable. Like you would have just spikes like this. So we do some aggregation, and we're going to show them 1 point per day instead of 1 point per second. So there are a few ways we could do this. We could load the high resolution data on the fly and do the aggregation on the fly. But that would be very slow because we'd have to load 5 months of high resolution data. We'd have to do the aggregation. So queries would take minutes. So what we do instead is we have a batch pipeline that I call the rollups pipeline that is going to pre-aggregate all of the metrics data for all customers. And it's going to produce different aggregations, 1 point per minute, 1 point per hour, and 1 point per day. And the query system will know based on what time frame the user is looking at, it will know what's the best resolution it needs to look at to fulfill the query. So this pipeline is running on Spark. It runs every day and processes dozens of terabytes of data and trillions of points. And it's one of our critical pipelines because if it doesn't run for a day or if it's behind, then there will be gaps on the graphs, and so customer will not be able to see their historical data. So that's why it's very important that we make sure this pipeline is highly reliable, and I'm going to use it throughout the presentation to illustrate my point. So let's start speaking about the architecture of our pipelines. This is a simplified view of our big data platform. When I speak about data pipelines at Datadog, you should think Luigi and Spark. That's what we use. And I'm curious, like, how many people are using Spark in the room? Cool, yeah, that's a lot of people. And how many are using Luigi? Cool. So if I start from the bottom, we're using AWS S3 as the persistent storage layer. It's been working really great for us. It's cheap, it's highly reliable, it has good integration with all the languages you can think of. So that's where we persist all of our data. On top of this layer, we have the clusters where we run the Spark jobs. And we use AWS EMR, Elastic MapReduce, to provision the clusters, install what we need on the clusters, and shut them down when they're done. And one thing we do, which is a bit unusual, is we have multiple ephemeral clusters. So that's why I added several times EMR. But I'll come back to that afterwards. And on top of that, we built a custom platform to interact with the clusters and with the jobs. And this platform has two types of workers. As I said, we're using Luigi for the task and workflow management. And there's the Spark worker, which is just in charge of compiling the code and sending the code to the right cluster and making sure that the job is running. And the users can interact in different ways with the platform using our web interface or using the CLI, and there's a scheduler for scheduling recurrent jobs. And we use Datadog to monitor all of these layers. I want to focus more on the clusters layer because we're doing a few things that are a bit unusual and that really impacts how we architect our data pipelines. So as I mentioned, what we do is we're using many clusters. So instead of, in a lot of companies, you'll still see one giant Hadoop cluster, and people will all run their jobs on the same cluster and they will compete for resources. We don't do that. What we do instead is that each pipeline is going to start its own cluster, it's going to run on it, and then when it's done, it's going to kill the cluster. So as a result, we have dozens of clusters that are running at a given point in time. This is a snapshot of the host map in Datadog, showing all the different clusters that we have. And each cluster is very short-lived. It has like a lifetime of about 3 hours on average. So we do this because it has several advantages. The first one is that we have total isolation between the jobs. So we know when there's an issue, we know why it's happening. Like we know what job is causing the issue. Whereas if you have dozens of jobs running on the same cluster, it may be harder to figure out what job caused the out-of-memory errors or what job caused the disk space issues. So isolation is good. We can also tailor each cluster for the need of every job. So if we have a job that is very CPU bound, we're going to use the C3 instance family in AWS if you're familiar with it. Or if the job is using a lot of memory, we're going to use R3 instances. We can also tailor the size of the clusters for each job. And it's very useful in different situations, like if we're behind, for instance, we can just push a button, double the size of the cluster, and we'll be able to catch up much faster. It's also useful as we grow. We can scale up the size of our clusters as the data volume increases. And people don't need to wait on loading clusters. So if a data scientist or a data analyst wants to run a job, analyze some data, it can just start its own cluster and shut it down when it's done. It doesn't need to wait for resources to free up on the giant cluster. And the last advantage is we can do easier upgrades of EMR, Hadoop, and Spark. These are usually painful to upgrade because stuff will break, new bugs are introduced. So what we can do here is do the upgrade on a single cluster first. We're going to test that everything works fine. We're going to let it run for a little while to make sure that it's okay. And once we know that everything looks good, we can gradually upgrade all the other clusters. Something else that is pretty unusual is that we are using spot instances for all of our clusters all the time. So if you're not familiar with spot instances, basically AWS needs to have a lot of servers sitting around to be able to serve the capacity of their users. But those servers are not always being used. So what they do is they put them at discount on the spot market. And you can use these instances at a ridiculous price. So usually we get up to 80% off the on-demand price. But the big downside is that nodes can die at any time. So you're not sure that you're going to be able to keep your nodes for the length of your job. So you can think of it as having basically chaos monkeys running all the time in our clusters and killing nodes randomly. So you're probably wondering, like, how can we build highly reliable data pipelines with instances that are killed randomly all the time? It's actually not such a bad thing, because it forces us to build our jobs in a way to make them fault tolerant. And the first implication is that we cannot have any long-running jobs, because the longer the job and the more work you're going to lose on average, and the longer the job, the longer it's going to take to recover from a failure. So a quick illustration: if you have two jobs, one is 9 hours, pipeline B is cut into 3 separate jobs that are persisting intermediate data. So if you have a failure after 7 hours, you're going to lose 7 hours of work, and the job is going to finish after 16 hours. Whereas in pipeline B, the first 2 jobs are done, the data is persisted, so you only lose 1 hour of work, and so you'll be able to finish after 10 hours. So you need to break down your jobs into smaller survivable pieces, and there are 2 ways you can break them down. The first way is vertically. So you're going to identify major transformations in your jobs, and you're going to persist intermediate data in between transformations. And the second way is horizontally. You're going to partition your input data, and each partition is going to be processed in its own independent pipeline. So that's what we did for the rollups pipeline that I presented in the introduction. So if you remember, we're taking some raw time series data as input, and we are producing aggregated time series data in S3 as the output, using a custom file format that we built for optimizing queries. So we could have a single job for that, but it would be huge. It would take more than 15 hours, so it's not great for fault tolerance. So there are actually 2 steps in this pipeline. The first one is the pure aggregation of the data, and the second one is storing and converting the data to our custom file format. So we broke it down vertically. So now we end up with 2 jobs. The first one is persisted the aggregated time series data in packets in S3. And the second one is doing the conversion to the custom file format. So okay, it's good. We have 2 jobs, but it's still not good enough, because as we'll scale, both jobs will get bigger, and they will be too big at some point. So we also partition the input data. The input data is actually coming from Kafka, so it's already partitioned following the Kafka partitioning scheme. And on top of that, we created another abstraction that we call the shards. So a shard is just a group of Kafka partitions, and each shard is going to be processed in its own pipeline. And so if a shard is getting too big, we're going to be able to split it very easily. So we end up with, in this example, 8 jobs instead of a single big one, which is much better for fault tolerance. So this approach is not free, though. It's a trade-off between fault tolerance and performance, because launching multiple jobs has some overhead. That's the first thing. And the second thing is persisting data to S3 is much slower than keeping the data on disk in HDFS or keeping the data in memory. So you need to think about the trade-off between fault tolerance and performance. A few lessons out of it. So we use many clusters for better isolation and easier monitoring. But as a result, we need to break down our jobs into smaller survivable pieces and persist intermediate data in S3. And keep in mind that it's really a trade-off between performance and fault tolerance. So now I'm going to talk a bit about how we set up monitoring on these data pipelines, what type of metrics we look at, and how we can detect failures early enough so that we can recover before the deadline when they happen. So as we saw, we use many ephemeral clusters, and on all of the nodes in the clusters, we install the Datadog agent, which will collect all system metrics, logs, and traces, and send that to Datadog. Now, these metrics, this data is only useful if you can look at it cluster by cluster. And so what we do is we tag the cluster, by the name of the jobs usually. So you have the rollups cluster where the rollups pipeline is going to run. You have the anomaly detection cluster where the anomaly detection job is going to run. So we attach the tag when starting the cluster in EMR, and then the Datadog agent is able to pick up that tag and attach it to all the data that it collects and send to Datadog. And so that's how we are able to then filter our data in Datadog and see the data cluster by cluster. It also gives us a permanent view of the clusters, because if you have a job that runs every day on a different cluster, so the cluster ID will change, the cluster information will change, but the tag will remain the same. So we can look at the metrics over a single month, for instance, thanks to the single tag that remains consistent. So we look at different types of metrics. The first types is obviously cluster and system metrics. So we have dashboards with like all the system metrics that we care about, but there are a few metrics that we care more about because they cause like common failures in our jobs. The first one is obviously disk usage. So we have a monitor set up to get alerted when nodes are running out of disk. So you see that the first 3 jobs are totally fine, like all the executors are way below the limit. But the last job, some executors are reaching the limit and the job probably failed on an out-of-disk error. So if we get alerted early enough, we can scale up the cluster and keep the job running. Another thing we look at closely is memory usage, as it's pretty tricky to manage in Spark. And there's an integration in the Datadog agent that lets us collect fine-grained JVM metrics. So we can have like the memory usage by container in the Spark job. So that's what you see on those graphs. And what you see is on the graph at the bottom, some containers are reaching the limit and then dropping down, so they're running out of memory, and the job probably failed because of that. Another thing we look at closely, as I said, we use spot instances. So we lose instances all the time in our clusters. And when the spot market is really unstable, all of our clusters will be basically failing and jobs won't be able to run. So when that happens, we basically need to switch to on-demand nodes. So we'll pay more money, but at least we're sure that we're going to make progress in our jobs, and we know that it has to happen from time to time. So we have this metric that tells us how many nodes are killed by EMR, and so we get alerted when this number is too high. The other types of metrics that we look at are work job metrics. The system metrics are good, but they don't tell you anything about what's going on exactly inside your job. So first we look at Spark metrics that are collected by the agent. And there's one that is especially useful for us, which is the number of failed tasks in Spark. Spark has a good mechanism to retry failed tasks, but like for instance when we're losing too many spot instances, it would keep retrying, and tasks will keep failing, and the job will basically get stuck. And so the only way to fix this is to stop the job and rerun it on another cluster. So we have an alert set up on that to know when too many tasks are failing in our jobs. We also collect custom metrics inside the jobs in between major transformation to know like exactly what's going on inside the job. So this is an example from the rollups pipeline. So this is written in Scala, and what you see is we're creating an accumulator that is going to count how many points are being processed in this transformation. And we do that for all major transformations. So that lets us see a graph like this. So we know that like if every day we're processing about 1 billion points, but then the next day we're processing only 1 million points, like we know there's something wrong in that stage. So we can identify exactly where the issue happens. We also collect things like how much time it takes to do some computation. So in this case, how much time did it take to merge 2 time series together? And that lets us identify potential skews in the data. Job metrics and system metrics are good for the data engineers, but they don't tell you anything about the global picture. If you remember the definition of reliability that I gave at the beginning, we want the data to be ready before a certain deadline. And so to know if we're behind or if we're on time, we also monitor data lags. So we have an app that will look in S3 and that will report in Datadog the data lag, which is basically when was the last time that the data was updated. And then it's very straightforward to set up alerts on that. So we're going to set up an alert like a couple of hours before the deadline so that we know if the job is running behind, and we have time to take some action to make it faster, like double the size of the cluster, for instance. And this is the type of metric that you can actually show to the customers of your data, because they don't care about how your job is doing, they just care about when the data is ready. So we provide these metrics internally to people that care about the data that we produce. So a few lessons out of this. Try to measure as much as possible. It's good to have all the metrics, because when there's an issue, you have full visibility on what's happening in your job. So it's very helpful for debugging. Set up alerts on the most meaningful metrics. And these alerts should be actionable, so that people should know exactly what they should do to fix the problem. And have some high-level dashboards with data lags, so that in a single look you know the state of your different data pipelines. So okay, we know how to detect failures, and failures will definitely happen. So you need to get prepared to handle failures, to be able to recover as fast as possible and finish before the deadline. So I'm going to talk a bit about what tools we have to recover fast from failures, and how we can limit the customer impact of failures. So your data pipelines will break, definitely. There are a lot of things that could happen. There could be hardware failures, especially if you're using spot instances. Instances will fail all the time. Clusters will fail. If your data volume is increasing, there will be new performance issues in your job, out-of-memory errors, higher disk needs, things like that. You're also depending on some input data, so it could be delayed, it could be corrupted. And finally, people are making code changes to your jobs, and so they could break stuff in the pipelines. So to deal with those failures, you need to keep two things in mind. You want to recover fast, to finish before the deadline if possible. And if you can't recover fast enough, you need to think about how you're going to limit the impact of the failure. Can I keep my functionalities operational at the cost of performance and efficiency and accuracy? So to recover fast, I talked a bit already about these points. You cannot have any long-running job, because failures will make it much longer to recover. When there are spot instability, we have the option of switching to on-demand clusters, throw more money at the clusters, and we can always double the size of the cluster or add more nodes as we need to if we want to catch up faster. Now, another thing you need to think about is how you're going to rerun your pipelines. This is useful when your job is running fine, but it produces some bad data or some incomplete data. And then, so you're going to need to rerun the jobs. It's not always trivial, so you need to think about it ahead of time. So it's not trivial because you need to think about, like, where is the data written, where do I need to clean up stuff? Is the downstream user already using the data? Is it okay if I simply delete it, even though he's already using it? So you need to think about it ahead of time. So if I go back to the rollups pipeline, it's one of these pipelines where rerunning jobs is not easy. So we had to think about this ahead of time. So if you remember, we're producing aggregated time series data in this pipeline. The aggregated data is actually written in 1 month block. So every day when the pipeline runs, it's going to process 1 month of data and write the updated data in S3 in a block of 1 month. We can't overwrite the data every day in S3 because the data is being used by the live query system. And if we overwrite it, there's an amount of time when the writes happen where the data would be corrupted. So we can't directly overwrite it. So what we do instead is we kind of version the data, and so every day the pipeline will write to a new location in S3. So as of with the dates when the pipeline ran. So you can think of it as a versioning system where you have different versions of your data. And then we have this concept of active location, which is just a pointer to the latest updated data. And so it tells the query code what's the data that it should use for each month. So if we're on the 22nd of May, the job is going to run, it's going to write to a new location, and once it's done, it's going to switch the active location to the new version. So what's nice with this system, the first thing, it's easy to revert to previous versions. It's just a matter of changing the active location. So if we realize that data is bad for the 22nd, we just update the active location and point it to the 21st of May. And the second nice thing is that it's easy to rerun the job. It's just a matter of, we basically increment a number appended at the end of the location, and then update the active location. So if you can't recover fast enough, you need to think about how you're going to limit the customer-facing impact of the issue. And the first thing is to try to isolate issues to a limited number of customers. And we can do that because we split the pipeline horizontally. So since we split the input data in different shards, we know what customer is in what shard. And so when there's an issue, we know what shard is affected, shard C, for example. So we know that the other customers are not affected. And we can contact the customers in shard C, for instance, to give them more information about what's happening. And then we also have a degrading mode for this pipeline, meaning we want to be able to keep the functionalities operational at the cost of performance of accuracy. So even if the pipeline is late or if it failed, we still want our customers to be able to query historical data. And so what we can do is basically tell the query code that, okay, our pipeline is late. Don't use the aggregated time series yet. Instead, keep using the high resolution data for this period of time. So what it means is that customer will still see their data on the graphs, but it will be a little bit slower because we're using high resolution data and we're doing more computation on the fly. But at least they will still see the data, and alerts will still be operational. Another issue we've seen in our pipeline is that sometimes we have like a very small number of corrupted files. And so these files would make the whole pipeline fail. So, which doesn't really make sense for us. Like, we prefer to have most of the data good for all customers, and only like a few metrics that are affected by the issue, rather than failing the whole job and affecting all customers with the issue. So we added a parameter in our jobs that lets us skip corrupted files. And that way we can basically let the job run and then fix the issue, investigate why there are some corrupted files, and then rerun the job once we know what the issue is and once the issue is fixed. And we can do that because we have good monitoring. So we know how many corrupted files appeared in the job. We know what customers are impacted. Whereas if there are too many corrupted files in the job, you shouldn't ignore those files because that's probably a widespread issue, and you need to fix the issue before running anything. So a few lessons out of this. Think about the potential issues that could happen in your pipelines ahead of time, and get ready to handle those failures. So have tools to recover fast, and have tools to limit the customer-facing impacts. So I'm getting to the end of this talk, and I think if you had 4 things to learn out of this presentation, it would be these 4 points. The first thing is know your time constraints. The time you'll need to invest to make your pipeline reliable will be highly dependent on how much time you have to produce the data. So if you have 3 days to produce some data, obviously you won't spend as much time to make the data pipeline reliable, as if you have only 2 hours to produce the data. So know your constraints. The second thing is break down your jobs into small survivable pieces. A good rule of thumb for us is to have jobs not bigger than 1 or 2 hours. That's the maximum we have. And monitor as much as possible. Collect system metrics, job metrics, and data lags to get the global picture. And think about failures ahead of time and get prepared to handle them, to recover fast, and to limit the customer-facing impacts when you can't recover fast enough. Thanks a lot for listening. We're hiring in my team in Paris and New York, and also in a bunch of other teams. So if you're interested to work with us on large-scale data pipelines, come talk to me, come to our booth downstairs, or shoot me an email, and I'll be happy to answer your questions. Thank you. Any question?
Yeah, you mentioned about degrading gracefully when you know the output of jobs is not correct. How do you know that the job output is not correct?
Yeah, that's a good question. I didn't talk about that, but we have some. So in the case of the rollups pipeline, we actually produce some dial tone metrics, and then we have an ad hoc check that runs all the time, and that basically run queries on the dial tone metrics. And that's how we detect bad data in this job.
Okay, I have one more question, which is you also talked about spot instances going down. Have you considered using, like building a cluster which is hybrid, like partly spot instances and partly on demand?
Yeah, we're not doing that right now, but that's something we're going to explore very soon, yeah.
Okay. Thank you.
Thanks.
Hi, one of your, over this way.
Sorry.
It seems like you're mixing operations and data engineering. Are you a DevOps? Are you data ops? Are you really mixing that?
Kind of both, I guess. We don't spend most of our time just maintaining our jobs, though. They're pretty self-sufficient. So I'd say we'd spend like 20% of our time fixing job issues, maintaining clusters, stuff like that, but we still spend 80% of our time developing new features, developing new jobs.
So there isn't a separate operations team?
Not for the ad hoc pipelines. This is in the same team.
You launch lots of on-demand clusters, small, maybe not small EMR clusters, and how long it take to launch it?
To launch a cluster?
Yeah, to set up it.
It's about 10 minutes, 5 to 10 minutes.
Okay, and do you have some small jobs that don't take like several hours and maybe several minutes? Do you have such tasks? And how you handle it, if you have it?
We don't have too many small jobs because usually like the data volume process is pretty big. So yeah, our smallest jobs are like 1 hour maybe.
Okay, thank you.
Thanks.
Hello, thank you for the talk, very interesting. I had a question about pricing, about the spot instances. So if I understood correctly, your pipelines are created when a user does something in production, so it's like kind of like real time what the user is looking for, then you create the pipeline to calculate that, is that correct?
Sorry, can you repeat the end?
Yeah, if the pipelines that you're mentioning, they are related to user activity in production, is that correct?
Yes.
So I have a question about pricing. Like, what is the strategy that you follow to establish the pricing to say how much a spot instance is gonna value for you? How do you establish the threshold to say, okay, now we go on to on-demand instances? And is that something that varies every day or every hour, or is that something that you have figured out and is basically established price because you know that's what's gonna work for you?
Okay. So our strategy right now is to set our bid price for spot instances to the on-demand price. So we're going to start using instances when the demand is higher than that. And we're switching to on-demand when we're too close to the deadline, basically. So when we know that we won't have time to recover, we'll switch to on-demand clusters. And that happens from time to time, but like not every day, definitely.